Alright, so I prepared a few problems as I told you I would. But before I go through the problems, I wanted to remind you that we have a pre-calculus textbook, right? You got this one at the very beginning of the year. And we are in this textbook, we're in chapter, oops, you don't see it, in chapter 3. And if you go under chapter 3 and you just kind of, look through, first of all, it has all the parent function, wherever we're talking about this is logarithm, you have the parent function and their characteristic. If you flip a few pages, you're going to have the same thing for the exponential. Okay, I'm not going to find it, but you know how to flip right there, right? Exponential function, this is when I have a base b, and then if you go to the next page, you have the one with the base e, the natural exponential. And again, you have examples on everything we've done, and you're going to recognize some of those problems because I actually used some of those problems as some of our examples. And if you go toward the very end, so look through, and you're going to see a little bit of everything you need, really. Some of the basic properties of logarithms. If you keep going in logarithms, so we're going to have the how to condense or expand, right? The properties of logarithms there. With some examples, the change of base formula is there as well. And you have problems, and then in the back of the book you're going to have the answer of all your odd problems, right? So logarithmic and scaling and semi-log plot is there too. So I would suggest that you get your book out, right, and kind of use it as a review as well. If you keep going toward the end there, you're going to have the chapter review, right? No, chapter review right there. Chapter review will be on page 315. So please use your resources, right? You have that book. Make good use of it. Okay, now for our problems. So I picked a few. Hopefully they're going to be helpful. The first one, maybe you should see it completely, is about fishing season is about to start. So my son told me he was going to go fishing tomorrow, which I think is silly because he lives in Utah and it's still snowing. Anyway, so I decided to go with one of those problems. So starting in 2018, a biologist studied the population of largemouth bass in a particular lake over several years. In 2019, that will be t equals 1, so they're telling us what to use, right, for the input. There were 430 largemouth bass. Now I'm going to kind of make a note of that. So in 2019, when t equals 1, I had 430 largemouth bass. And then in 2023, and they're telling me that when t equals 5, I had 715. And we are told that this can be modeled with this equation right there. And notice how that's a logarithmic equation, right? Okay, so we're going to have to build that using what they give us here. So when we don't know, we just, first of all, let me use a different color so we can see it better. So I'm just going to write down my equation first. Okay, then I'm going to use my first point. T is 1, and then the L of t, my output will be 430. So I'm going to substitute those values in. Don't know what A is, don't know what B is yet, but this is 1. Well, that's kind of really cool, right? Because when you have a 1 in an argument of the natural log, you know that the whole natural log is 0. And if that's all 0, 0 times b is 0 as well, so that whole thing just goes away to 0. And I'm left with my a value. Well, I'm making progress. Know what a is. Okay. Now, I'm going to use my second point they gave me. Oops, this one's not working. So use the second point they gave me and use my equation again and just plug in and see what I can get from that. So my L of t, my output will be 715. My a value I already know, so I'm going to use it, right? So I know that's 430. B, oh sorry, forgot my b. B I don't know yet, and then the natural log of 5. Okay, now natural log of 5, I cannot do that like that in my head, right? I would need a calculator. So let's make our way to it first. So I'm going to first subtract 430 from both sides. And then I'm going to divide by natural log of 5. So that first will give me 285. And I'm left with b times the natural log of 5. And I need to get b by itself, right? So I'm going to divide by my natural log of 5 on both sides. Now that's going to give me a decimal, right? So you just put that in your calculator and you're going to get a decimal. And I did it earlier, so let me find it on my paper here somewhere. I found that b is about equal to 177.0805. Okay? I have a and I have b, so now I can write my equation. So my equation will be L of t equals the a value, which is 430, plus my b value, which is 177.08. I'm going to change that to a 1 here, and then times the natural log of t, my input variable. This is my equation right there. Now, what if, so I mean there are some more questions and I really am not going to go through all of those, but what if now I wanted to know when am I going to have 1,000 largemouth bass in the lake? So what at time t, for what at 1 year we're going to reach 1,000 population, according everything just keeps going the same way, right? Okay, so to do that, I'm actually going to put that in my calculator. So I'm going to say, well actually, yeah, we don't need to put it in the calculator, but I just want to show you, so I'm going to do it anyway. Alright, so in the calculator, I'm going to enter my equation. So in y equal, I'm going to say I have 430 plus 177.081, we said, times the natural log of x, right? We're going to use x in the calculator. And below, I'm going to enter the 1,000. And now I'm going to graph all of that. Now, obviously, this is not going to show, right? Because this goes from negative 10 to 10, negative 10 to 10. Well, my numbers are way bigger than that, right? I have a y-intercept of 430 just to start with. Okay, so I'm changing my window. So for my window, time 0 negative wouldn't make any sense, right? So I'm going to start at 0. And then I don't know where I'm going, so let's try 50 and go up in 5s. Then the y's, well, I don't need any negative value because I'm not going to have a negative number of fish, right? So 0 would be good. And then for the max, well, I need to be at least above my 430 there, right? And literally. Oh, and I want to know when I'm going to have 1000, so I need to be bigger than 1000 there. So let's go 1500, and let's go up in 100s. Okay, let's grab that. So here it goes, and here it goes. You see? So this is the model L of t, this equation that we came up with, and then this is my 1000, and I'm looking for that intersection point. So I'm going to go second, calculate, and if you're reading through the menu, you're going to say that there is an intersect there. That's what I want, number 5. And then the calculator asks me, am I on the curve? So if you're not sure, just move it a little bit, but there are only 2 curves, right? So we're going to be there. Enter, and then it jumps to the other curve. See how it's on the red line now? So I'm going to say, yes, you're on it, enter, and then it always asks if you want to guess, you always enter, you don't want to guess. Okay, we're going to have 1000 fish when t is 24.999. So I'm going to say 25. So we're going to have 1000 fish when t equals 25. And that will be 25 after 2018, right? Because we're starting the year 2018 is my year 0. So, yeah, because 2019 is 1. So 2018 plus 25 would be in year 2043. Okay, that's when I'm going to have 1000 fish in the lake. Alright, so that was for that. Switching. Now I want to just very briefly talk about that. So when you're given a graph like that, the first thing you need to look is that a semi-log plot, or is that just a regular Cartesian XY plane? Well, my x-axis, the units are going up by 1. But when I'm looking on my y-axis, I'm going up by powers of e, right? I have 1, then e to the second, e to the third, e to the fourth, etc. That's a logarithmic scale. So that's a semi-log plot. So when I'm looking at that equation, that pretty much looks like a straight line. Because this is a semi-log plot, and it's linear, that means that before we change that scale to a logarithmic scale, this used to be an exponential function, right? So used to be an exponential function, and my points here are going up, meaning my exponential function was growth, not decay. If my exponential would have been decay, then that would go down with a slope, negative slope from left to right. So I'm looking at my equations here, and I'm going to try to figure out which one works. Well, this is not exponential. This one is, but I have a plus 2 here. So now I need to figure out what's happening here with that point. This is my y-axis, right? And when x is 0, I mat looks like 2, right? Because if that's e is 2.7, so that would be about 2. Well, if I plug in a 0 here, I would have a 2, wouldn't I? But what if I plug in a 1 here? I would have 2 plus e. And that's not 2 plus e, because remember, this is not going up by equal units, right? It's logarithmic, right? So what you want, and we said the original function was exponential, so we are looking for something exponential. Growth, that's the one I want, because this would be decay. The negative exponent would make me rewrite that as 1 over e to the x, and then that would be less than 1, therefore decay. Okay, I just wanted to quickly kind of just talk about that. Alright, where am I going? Now, this one is similar to number 3, the one that you guys struggled a little with, right? This guy, remember? Okay. So what I did to save some time is I went ahead and already entered all of those numbers in my calculator. So what are we talking about here? we're given values that are representing the life expectancy in years and the income in $1,000 per year, right? So that represents $2,000, $7,000, etc. And then this will be the life expectancy in some countries. And what we have to do is we need to come up with a logarithmic regression. Now, remember, here we were told in words, find a logarithmic regression, right? For that. We are not told in that many words here, but they're giving us the model, and when you're looking at the model, I sure see that natural log there. So this is a logarithmic model I need to come up with. So I already have that in my calculator. So I go Stat, Edit, and sure enough, right, I entered those in my L1 and L2. So I'm good there. I'm going to make sure my stat plot is turned on, so second stat plot, and it's not, so I'm going to turn it on. And I'm checking to see if I have L1 and L2 here, and I do, so I'm good to go there. I'm going back to my home screen. Now I go Stat, over to Calculate, and we want the logarithmic regression, right? So number 9 there, the natural log regression. So number 9, L1, L2, so I'm good, and I'm going to have that equation saved in the y equal for me, so I don't have to type it in by hand. So the variable key here, over to the y's, right, y bars. Number 1 function is good, and then y1 is good, and I'm good to go. Okay, so first of all, I'm looking my regression there. Looks like it's going to be a pretty good model. The top line, I remember we said, always gives you the model, where you put your values in, right? So the A and then the B, and then they give you the values you need. So what we would need here is that I'm using L of x because that's what I'm given. So L of x equals the A value would be 56.8135. I'm going to keep 4 digits, and then plus B, and B is 6.53385. So we're going to go with 9 and then times the natural log of x. Okay, so that's my model that the calculator gave me. And then I'm supposed to use that model. So in 2009, the United States had per person income $41,256.10 and a life expectancy of 79.43. And we want to know, is our model going to give us anything close to that? So we're going to check that out. So remember, your income is your input, and this will be your output, right? If I want 41,256 in income in thousands, then I want 41, right? 0.2. 0.256, I'm going to go 41.3 is going to be my x value that I'm going to use. Okay, so I asked the calculator to save that for me here, right? And I'm going to use it now. So go to my home screen. I'm going to call, now remember, y1 is where that equation is, right? Home screen. And I'm going to call that y1 to my home screen. So vars over to the y, number 1 function, and then number 1. And in that, I want to enter an x value of 41.3, right? So this is a function now, right? And I'm going to enter 41.3, and the calculator is going to give me 81.12, and the real number was 79.43. So a little bit higher than the real number, right? And by the way, that's what we call the residual, right? The value you get from your model and the value you get from real life, from the data, when you subtract those, the difference between them is called the residual. Okay, that's enough on that one. Then, if I'm given this expression and I need to write it as a condensed single logarithmic form, I'm going to look and see. So it's the subtraction between them. That means I need one single log, right? One single logarithm. We have a subtraction, so we take the arguments and we divide. So we divide the first divided by the second. So 6x divided by 3. And then we're going to simplify that, and that will give me 2x. So this expression is equal to what we started with. Those two are equivalent expressions. Okay, here we need to evaluate, not using a calculator, just using our properties and what we do know. Now, I have a 1/2 here, and I don't like that 1/2. So I'm going to change that to a base 2. Okay, so you ready? I want to change that to a base 2. So I'm going to have a log base 2 of my argument divided by a log my new base I want, and what used to be my base becomes my argument here. Okay, so again, this is the same thing as doing log, and if I had a b here and an x there, and I wanted to change that base b to maybe an a, I would have a log base a of x divided by log base a of b, what used to be my base, right? That's the property, the formula. Okay, so back here, I'm looking at that and I'm thinking, oh, well, look, base 2, argument 2, that goes to 1, right? 2 to what power gives me a 2? That's a 1. So in the numerator, all I have left is a 1. Now here, we almost see it. Some of you might already see it, but I'm going to rewrite it. Instead of having a fraction, I'm going to rewrite that as not 1/2, but 2 to the negative 1, okay? And because that's now 2 to the negative 1, I have the base and the argument that are the same, so that goes to 1. This exponent I'm going to take and bring to the front, and so it will be just 1 over negative 1, which is just going to be a negative 1, okay? Alright, now some of you asked me for something that's similar to this one, right? That was number 8 in the review, so there is one similar to that. So I'm given a function f of x, and it's x minus 2 quantity squared minus 3. We need to restrict the domain so that f of x is a one-to-one function, so that we can find an inverse that's also a function. Then we're going to find the inverse, sketch both of the graphs, find domain and range, okay? Alright, so I'm going to start graphing that. Parent function is quadratic, but it has been moved to the right 2 and down 3. So quadratic used to be here to start, but I'm moving to the right 2 and down 3. So I'm right there. And technically, there is no vertical stretch or compression, so it's a quadratic. I'm going to go up 1 over 1, both directions, and then 3 over 1, and then 5. 1, 2, 3, 4, 5. Remember, when we do a quadratic like that, we do that. And then I'm just going to graph my parabola as good as I can, and I am not going to graph the other side, because the other side should be there, right? But I don't want it because I need to restrict the domain so that I have a one-to-one function, right? One-to-one means I need to be able to pass the horizontal line test, so I need to keep just the one right-hand side of that parabola. So this is going to be my transformed, my restricted f of x, right? So this restricted f of x has a domain, of 2, right? Starts at x equals 2 and it keeps going forever to infinity. So 2 to infinity. 2 is included. We actually start there, right? So we put a bracket. And then the range will be, well, my lowest value will be -3 included, and then it's going to shoot up to infinity. Okay, domain and range done. What's pretty cool now is that I can say, hey, now I can actually do domain and range of the inverse function as well. Might as well. So the domain will be what used to be the range, so from -3 to infinity, and the range is what used to be the domain, so from 2 to infinity. Okay? Alright, now what else did we need to do? I need to sketch my inverse. So I can sketch my inverse by finding it first and then sketching it, or I can just use my points, right? So this here is the point 2, -3. So when you flip that, it'll be -3, 2. So 1, 2, -3, and then +2. So my first point is right there. My next point is this one, and that will be 3, -2. When I flip that, I'm going to be at -2, 3. And then I can do one more point, but I could really count, right? 1 over 1, and then it will be 3 over 1. So I will be here, and then 5, 1, 2, 3, 4, 5 over 1. So that will be my graph of the inverse. And then if you want to check, right, put your symmetry down, your line of symmetry, which should go right there. And if I erase that one, which we didn't want because we restricted, then you can see how those two are symmetric over the line y equals x, right? That's the line y equals x. And the green one here is my f inverse of x. Alright, so we have it graphed. Now we actually need to find it algebraically. So we need to go back to our function. We're going to call the f of xy, and then we switch x on y. Ready? So that becomes an x. That becomes a y. Now I'm going to add 3 first, so x plus 3. Then I need to get rid of that square, so I'm going to take a square root on both sides. And then I'm going to add the 2. Make sure that 2 is not inside the radical, right, because it shouldn't. And that's equal to y, which really that's my f inverse. So I'm going to write that properly now. So it will be square root of x plus 3 and then plus 2. There we go. So that's for this one. Then I had another request, something that would be similar to, I think it was the one just below it. Yes. Somebody asked me something similar to number 9, so there is something similar to that. Okay, so we need to graph f of x. So I'm given a function here, and that's an exponential function. So we need to kind of remember that parent function of exponential are always going to have a point at 0, 1, and then whatever the b value is when x equals 1, right? So the parent function of that's a b value of 3, so the parent function would have at x equals 1, we will be at 3, so we will be up here. So this exponential parent function would look like that, okay? Now we need to apply those transformations to that parent function. So y-intercept used to be right there, and I'm going to have to move it to the right by 1 and then up 2. So take that point here, right by 1 and then up 2. that point here used to be at 1, 3, right? So 1, 1, 2, 3. I'm going to move it to the right one, so here and then up 2. So it goes right there. Now there is one more thing we need to be very careful here, and that's the asymptote. The parent function, the x-axis, stands for its horizontal asymptote. But that asymptote has been moved up by 2, right? Because we do a vertical shift up 2. So I need to make sure I'm not passing that horizontal asymptote, right? We can't go below it. And we're ready to graph. There we go. Oh, I'm not doing a good job here. That's better. Okay. And that will be f of x that we just graphed. Okay, so once I have it, it says, can you give me the domain and the range of both? But we don't have the other one yet, so we just do f of x for now. So the domain for f of x, I don't want to write here because I'm going to graph the inverse. Huh? So f of x has a domain. So the domain of any exponential is all real numbers, right? And then the range will be from the horizontal asymptote up to infinity. So from 2, right, up to infinity. Not including 2, right, because we're not touching the horizontal asymptote, so we're not going to put a bracket. Unlike what we did here, where we had the brackets, because that point was actually part of my graph, right? Here, we have a horizontal asymptote that we're approaching but not touching, so we don't put brackets. Okay, we have f of x done, so we are actually ready to do domain and range for f inverse. So the domain will be from 2 to infinity, and the range will be all real number, right? Just flip those. Okay, keep going. So we have that done. We need to use, okay, I need to graph the inverse. So I'm going to pick some of those points. So this point right here, let's do that in a different color. This point right here is the point 1, 3, right? So I'm going to need the point 3, 1. And then this point up here is the point 2, 1, 2, 3, 4, 5. So this one is 2, 5. So I'm going to need 5, 2 right there. And I have a horizontal asymptote here at y equals 2. Therefore, this one is going to have a vertical asymptote at x equals 2. So vertical asymptote at x equals 2. Okay, and you're ready to graph that. So let's do it this way. There we go. And if you put your line of symmetry here, your line y equals x, you will see that those two are symmetrical over the line y equals x, right? Alright, so we have the domain and we have the range given. We graphed them both, so we did that. Use the limit notation to describe the end behaviors. Okay, so for the f of x, for the exponential, as I'm going toward negative infinity, my function is approaching the horizontal asymptote. So for the purple one, the limit, that's for f of x, the limit as x goes to negative infinity of f of x is going to be equal to 2. Now it's never going to touch it, right? But the limits don't care if you touch, they just want to know what direction are you going, what are you approaching. And we're going to approach an y value of 2. And then on the other side, we need to say what does it do the other side, the limit, as x goes to positive infinity of f of x. And as we're going to positive infinity, that function just keeps shooting up. So it's not even an equal here, it's an arrow of infinity. Alright, now let's do the same for the inverse. which is our log function, right? Well, this one is not going to go to negative infinity for the x, right? Because it has that vertical asymptote it cannot cross. So it's never going to keep going to negative infinity. So we don't have that there. So where is it actually going? Toward the left-hand side. Oops, what am I doing? I'm writing a log now. The limit as x approaches, and the value it's approaching is going to be 2 here, right? That's my vertical asymptote. So limit as x approaches 2. From what side is it coming? Is it coming from that side or from that side approaching 2? It's coming from the right side, right? So we're going to do a plus here to show that. And that's for f inverse. And as I'm approaching 2, the function is shooting down to negative infinity. And on the other side, the limit. So on the other side, the function actually keeps going, right? So as x goes to positive infinity, f inverse of x also goes to positive infinity. And then we need to name a few characteristics. So you could say that f of x does not have any x-intercept. You could say that f of x is concave up, f inverse is concave down. Both of them are monotonic, right? They're never going to change direction. They're both increasing function as well, right? This one is increasing and this one is increasing as well. So I mean, you know, just pick some characteristics and give me a few. And I think that's all I had for you. Well, that's long enough. Well, study well, and I'll see you in class.